Let's keep going with the second right-hand rule here. So now we're looking at a current loop instead of a straight wire. So the related equation is the second one here. So this one tells us that if you have one or more loops, n is the number of loops, it can be one, that's fine, and r is the radius of the loop, and I is the current in that wire, then this will give us the field in the center of the loop. Now you could also have a solenoid, which are your loops that are closely spaced, your coil that has usually thousands of loops. Then n is the number of loops, L is the length of the solenoid, I is the current, and you can find the magnetic field in the center of that solenoid. So the right-hand rule tells us which way is that field. So let's say that the current is going counterclockwise. Then you curl your fingers that way. Right, so you've got your fingers curling this way, counterclockwise, and your thumb over here is pointing right at you. So there's your thumb right here, is coming out of the page. So that's the field coming out of the page. And this right-hand rule also works to find the magnetic moment. So instead of saying that this is B right here for the magnetic field, you can say this is mu for the magnetic moment. And that's going to be useful when we get to torque. So let's go ahead and do the third right-hand rule here. So this one is talking about a moving charge or current in a straight wire, and there's an external field, and then that moving charge or wire will experience a force. So it's more helpful to look at the right-hand rule first. So the right-hand rule tells us that put your fingers in the direction that the positive charge is moving, or the current. So let's say we just have a current that's going up. So the current. And then, so your fingers are going up. And let's say that there is a magnetic field going to the left here. So what you're going to do with those fingers that were up here, or your fingers were up, your thumb is again pointing right at you, pointing out of the page here, but you're folding those fingers to the left so that your hand actually looks like this. Got other fingers here, but you still have your thumb pointing out of the page. Thumb is pointing out of the page, so the fingers were originally going up for the current. They folded to the left for the field, and the thumb was out of the page, and that's the force. So this right-hand rule, it shows us that the force is both perpendicular to V and B, right? Out of the page is perpendicular to I, which is also V, the motion of the charge, and B. And if V had been parallel to B, there would not be any force on that charge or on that wire. So if the field had been going upward, then there would be no force on that current carrying wire. If you have a charge that is moving to the left and the field is going to the right, then there's still no force on that charge because they're along a straight line, they're parallel to each other. And really pay attention that the charge must be moving. If the charge is stationary, there's not going to be any force on it. Now there's a case where, let's say that your charge is moving perpendicular to that field. Let's say the field is going up into the page. And let's say the positive charge is moving up. Well, in that case, the magnetic force here is going to provide a centripetal force. If you do the right-hand rule, your V is up, the B into the page, you should see your thumb pointing to the left. And that force is going to cause the charge to move in a circle. And once you realize that V is perpendicular to B, that makes the charge move in a circle, then you should be able to use this equation right here to figure out how big is that circle. That depends on the mass, on the speed of the charge, on the amount of charge, and on that external field, which must be perpendicular to the velocity. Remember, if V is parallel to B, then it experiences no force, right? So that means if V is going here and doesn't experience a force, V is just going to keep going in a straight line. But if B is perpendicular, then your object is going to start moving in a circle. And the last thing about this is, remember that this right-hand rule is for a positive charge. So let's say that we now have a negative charge here, and the field is to the left, and this negative charge is moving up. Well, you're still going to use that right-hand rule. You put your fingers up, you fold to the left, your thumb is out of the page. But then because it was a negative charge or an electron, you make sure to say that the force is not actually out of the page. The force is actually into the page, because the force will always be in the opposite direction if you have a negative charge.